I'm Dr. Sarah Ballantyne, and this is the Autoimmune Protocol Lecture Series, Week 1, Lecture 6, The Causes of Autoimmune Disease. We've already discussed how autoimmune diseases have this sequence of events. Autoantibodies form, then the body's natural fail-safe mechanisms for detecting that the immune system has learned the ability to attack self, those fail-safes fail. Then you have something drive the immune system to attack, and when enough damage builds up to whatever tissues are attacked, that symptoms manifest, that's when you get a diagnosis of autoimmune disease. So now let's break that down and look at the causes of each of these different steps in the pathogenesis of autoimmune disease. So we already talked about how antibodies recognize a very small sequence of amino acids, 15 to 20 different amino acids in a chain. That's what an antibody actually binds to. And it's that small fraction of a protein that is what allows an antibody to determine that this is a virus or this is a bacteria or, oh no, this is some tissue in our body. Where autoantibodies come from is this accident that whatever that antibody is binding to, that sequence of 15 to 20 amino acids, is not just something in a foreign invader, but something in our bodies. Part of this accident comes from the fact that there's actually some commonalities among all forms of life. So, we're about 60% the same as earthworms, and we're over 99% the same as chimpanzees. There's certain proteins that are used across all forms of life. So if you have an antibody that binds to something that's fairly ubiquitous, it's going to bind to something inside our bodies in addition to a foreign invader. So that's one source of autoantibody formation, is just the commonalities among all forms of life. But there are other sources of autoantibody formation. I also already discussed that one of the sources of autoantibody formation is a mechanism for the immune system to detect cancer cells, that there's this totally normal production of autoantibodies that is actually necessary for helping the body detect that cancer cells have formed and helping the body eliminate them. But other sources of autoantibodies come from infections. So we know that there's certain infections that are strongly linked with autoimmune disease. So for example, Epstein-Barr, which causes mononucleosis, is strongly linked with a variety of autoimmune diseases. And this may be through autoantibody formation. So our body forms an antibody against that particular virus, and through the commonalities between all forms of life, that antibody has a high likelihood of recognizing some tissue within our bodies. So infection is a really common source of autoantibody formation. We also see autoantibody formation coming from dysfunctional immune system as it's going through tissue repair and cleanup. So if that aspect isn't regulating itself well, even cells within our body, as our immune system is cleaning them up, that can be a source of autoantibody production. We also see autoantibodies can be produced through food sensitivity. So for example, we develop an intolerance against gluten, very common, and dairy, very common, that the antibodies that we would produce against gluten or dairy recognize a tissue within our human bodies. And there's a fair amount of science to suggest that antibodies against gluten or against dairy in particular have a high likelihood of also recognizing tissues within our body and affecting us by targeting the immune system to attack tissues in our bodies. So in terms of infection, we do see these really specific links. So prior infection of certain types of infectious organisms increases risk of specific autoimmune diseases, and this may be through the production of autoantibodies. That seems to be the most likely scenario. And it's because of this commonality amongst all forms of life, these autoantibodies are derived from antibodies that recognize that infectious organism. So I already used the example of Epstein-Barr. We produce antibodies against Epstein-Barr. That happens to also recognize, for example, a protein in the thyroid gland, and that's why there's a link between Epstein-Barr and Hashimoto's thyroiditis. This ability for an antibody to react to more than one antigen or the same antigen on more than one thing, like a pathogen and a tissue in the body, this is called cross-reaction. So an antibody can bind to more than one thing. And we're going to talk about cross-reactive antibodies in some other contexts later in this lecture series. So Borrelia is a spirochete bacteria that is responsible for Lyme disease. It's also strongly linked to rheumatoid arthritis, sarcoidosis, schizophrenia, and dementia, which are suspected autoimmune diseases. So if you've ever had a diagnosis of Lyme, not even chronic Lyme, that may increase your risk of autoimmune disease through this autoantibody formation. Chlamydophila pneumoniae is a bacteria that causes pharyngitis, bronchitis, and atypical pneumonia. Previous infection with this increases your risk of arthritis, myocarditis, Guillain-Barré syndrome, Alzheimer's disease, chronic fatigue syndrome, chronic obstructive pulmonary disease, multiple sclerosis, and Tourette syndrome. Those are all autoimmune disease or suspected possible autoimmune diseases, like Alzheimer's is suspected. Enterovirus. These are viruses that cause the stomach flu, right? They're viruses of the gastrointestinal tract. They are very, very common, and yet they increase your risk of amyotrophic lateral sclerosis, chronic fatigue syndrome, type 1 diabetes, Guillain-Barré syndrome, again, and schizophrenia. Giardia is the parasite that causes beaver fever. And if you've ever had Giardia, you have a higher risk of multiple sclerosis, amyotrophic lateral sclerosis, Parkinson's disease, chronic fatigue syndrome, arthritis, and uveitis. H. pylori. This is the bacteria that causes chronic gastritis and dramatically increases your risk of stomach ulcers as well as stomach cancer. Having had H. pylori, which about 50% of us have, that increases risk of immune thrombocytopenia, psoriasis, and sarcoidosis. Herpes virus, which can cause a huge range of illnesses, such as roseola or Epstein-Barr is an example of a herpes virus and causing mononucleosis. Different types of herpes viruses are linked with different autoimmune conditions. So cytomegalovirus, or CMV, is linked with, again, Guillain-Barré syndrome and lupus. Epstein-Barr, I already mentioned it was linked with Hashimoto's thyroiditis, but it's also linked with dermatomyositis, lupus, rheumatoid arthritis, Sjogren's, and multiple sclerosis. And human herpes virus 6 is linked with multiple sclerosis and chronic fatigue syndrome. Norovirus, a very, very common disease that causes sort of severe stomach flu or gastroenteritis. It's linked with Crohn's disease. Parvo B19 is a childhood virus. It causes fifth disease, which is a rite of passage childhood disease. And a form of acute arthritis is also caused by this virus, but it increases risk, lifetime risk of developing rheumatoid arthritis, lupus, and vasculitis. Streptococcus, strep throat. It increases risk of developing Tourette syndrome. And Toxoplasma gondii, the parasite that causes toxoplasmosis. This is the reason why pregnant women are not supposed to scoop kitty litter to avoid T. gondii. Having T. gondii infection increases risk of Alzheimer's, Parkinson's, Tourette's, antiphospholipid syndrome, systemic sclerosis, and inflammatory bowel diseases. So we see all of these specific links between infections and certain autoimmune diseases. Autoantibody formation through cross-reactivity seems to be the driving mechanism. So a lot of those diseases are rite of passage diseases. Chances are that, like me, you can check off at least a few of those as having had them in your past. They're not things that you can prevent. So why does somebody have mono as a kid and develop autoimmune disease and somebody else doesn't? Well, this has to do with the fail-safes of the immune system. So as I mentioned, regulatory T cells are, and there's a few different kinds, right? So there's regulatory T cells, Th3 cells, and TR1 cells. All of these cells, their job is to rein in the immune system, to turn it off when the job is done. They are also responsible for detecting if another cell is attacking the wrong thing, if it's attacking us instead of the foreign invader. So these cells are really, really key in reining in the immune system. And they can control and regulate the immune system through a variety of interactions. So through the production of specific inflammatory cytokines, so mediators, these chemical messengers of inflammation. A lot of them are pro-inflammatory, they drive the inflammatory response, but some of them are anti-inflammatory. They help suppress the inflammatory response. And the ones that regulatory T cells secrete tend to suppress the inflammatory response. They can also cause immune cells to die. So they can impact what immune cells are actually alive and attacking something. They can compete with immune cells, so they can actually make it so that a dendritic cell, for example, can't present an antigen to an effector T cell because the regulatory cells are basically surrounding it and saying, no, guys, can't go over here. They can change the metabolism of other immune cells so that the immune cells can't do their job. And they can directly interact with effector cells, with dendritic cells, with macrophages to shut them down. And that interaction is done through cell-cell contact. So in a normal, healthy immune system, we have what's called homeostasis. We have a steady state system where there's a balance between effector cells, right, the cells that are attacking, that are able to defend our body against pathogens, but are also the cells in, say, autoimmune disease that would attack a tissue within our body. There's a balance between those and these regulatory T cells that are helping to rein in the situation. That's what happens under normal conditions. But in autoimmune disease, we lose that immune regulation. And that can happen in a few different ways. It can happen with an underproduction of regulatory T cell subsets, so we just don't have as many in the body to do their job. It can happen when those regulatory T cells just aren't they're there, but they're not active, so they're not good at controlling what effector T cells are doing. They're not producing their anti-inflammatory cytokines the way they're supposed to, for example. It can happen when the effector cells are unable to listen to the regulatory T cells. So there's some kind of resistance to those cytokines, for example. So the regulatory T cells are producing all their anti-inflammatory cytokines and the effector cells are ignoring it. So there's a lot of ways that this imbalance between effector cells and regulatory cells can occur. And when that happens, we lose immune regulation. So we lose the ability to rein in the immune system. We lose the ability to stop self-attacks, so attacks of the immune system on something in our bodies. And depending on what part of the immune system is not being regulated, we can end up with autoimmune disease, but we can also end up with things like allergies. And what's really interesting is if you skew things the other way, if you imbalance things the other way, so we have too many regulatory cells and too few effector cells, that imbalance in the immune system, that dysfunction of the immune system, is what's behind cancer and chronic infection. So really we want this balance. And in autoimmune disease, we're going to talk a lot about sort of ineffective or insufficient regulatory T cells and too many effector cells. But it's important that, we've got this give and take. We don't want to overcorrect. And this is one of the reasons why, for example, the new immunomodulatory drugs for cancer that are, one of the most exciting new drug developments for cancer, they work by dramatically suppressing regulatory T cell subsets and increasing effector cells. And one of the major side effects that's happening in patients who are taking those drugs is autoimmune disease development. So it's not just a matter of suppressing one side of the immune system and stimulating the other. It's about bringing back balance to the immune system. And that's why diet and lifestyle stimulus is so important, because it's not a direct modulator of one aspect or another. It's providing the resources for the immune system to regulate itself. And that's when the immune system functions at its optimal. So genetics accounts for approximately 1/3 of our risk factors for autoimmune disease. And unlike other conditions like cystic fibrosis, there's not one gene that we can point to that is the culprit behind autoimmune disease. Instead, it's a collection of genes that are influencing really how sensitive our immune system is to dysregulation. So it's a collection of genes that are going to make it so that our immune systems get overstimulated more easily, accidentally recognize self more easily, or don't have the ability to regulate themselves quite as easily. So where genetics come into play in autoimmune disease, it doesn't doom you to autoimmune disease if you have these genetic predispositions, but what it does is it increases the likelihood, because it increases the likelihood of an immune system that is going to dysfunction in the way that immune systems dysfunction in autoimmune disease. So right now there's upwards of 70 different risk genes that have been identified for autoimmune disease. And most people with autoimmune disease have a few of them. So let's go through some of the most common. RAG1, RAG2, these are genes that control receptor editing on B cells. So if B cells in the bone marrow are also tested. So if they react with self, they stay dormant inside the bone marrow. They're not released into the body. But when you have a variation in RAG1 and RAG2, that means that those B cells are still released, even if they fail the autoreactivity test. And RAG1 and RAG2 mutations are implied very strongly in SCID. FOXP3 is a molecule embedded in the cell membrane of regulatory T cells. And FOXP3 is actually one of the ways that biologists can identify those regulatory T cells compared to other T cell subsets. So other CD4 positive T cells don't have FOXP3. Regulatory T cells have CD4 and FOXP3. Mutations in this molecule prevent regulatory T cells from developing. So that's a really big deal. So if you have a mutation in FOXP3, you don't have as many regulatory T cells. And this is the culprit actually behind IPEX, which is a very severe and lethal autoimmune disease. Sialic acid acetylesterase, or SIAE for short, is an enzyme that decreases B cell receptor signaling and required for immune tolerance. And it's actually required for suppressing autoreactive B cells. So mutations in this gene mean that autoreactive B cells are no longer suppressed, they're released into the blood. We see mutations in this gene in about 2% of people with autoimmune disease, and it's particularly high in rheumatoid arthritis and type 1 diabetes. The Trex1 gene has an important function for proofreading DNA synthesis, and it is a component of a cytokine response to detected viral DNA. And mutations in Trex1 have been associated with AGS and Chilblain syndrome. And finally, the gene for PTPN22, it encodes tyrosine phosphatase, the tyrosine phosphatase non-receptor type 22, which affects the responsiveness of T cell and B cell receptors. So a particular gene mutation in PTPN22 is associated with type 1 diabetes, rheumatoid arthritis, lupus, vitiligo, and Graves' disease. So now there's a couple of genes that you may have heard of, and these are ones that have been really extensively studied in the context of autoimmune disease because multiple different variations of these genes are linked with different autoimmune diseases. So MTHFR you may have heard of because of its role in detoxification. MTHFR is the rate-limiting enzyme in the methyl cycle. So methylation is one of the ways that our bodies control whether or not proteins are turned on or turned off. So we use this, for example, in neurotransmitters. We use this in cortisol is turned on or off via methylation, melatonin. So some really important hormones turned on or turned off by methylation. And so the MTHFR enzyme encoded by the MTHFR gene controls how well we recycle those methyl groups. So defects in that gene impact neurotransmitter regulation, impact very strongly detoxification. They can impact hormone signaling in a variety of ways. We can get the buildup of a toxic non-protein amino acid called homocysteine, which dramatically increases inflammation. MTHFR is also important for the conversion of the vitamin B9 that we eat into the active form of B9, methylfolate. And so you can end up with vitamin B9 deficiencies, even though you're consuming plenty of it, if you have an MTHFR gene variant that decreases activity of that enzyme. So MTHFR mutations, and there are two key ones. These have been associated with type 1 diabetes, Hashimoto's thyroiditis, Graves' disease, rheumatoid arthritis, vitiligo, multiple sclerosis, Alzheimer's, and schizophrenia, in addition to a ton of other chronic illnesses like cardiovascular disease, renal disease, neurodegenerative disease, osteoporosis, and cancer. So having a variation in an MTHFR is definitely a genetic predisposition to a variety of chronic illnesses. It's not a life sentence to develop those chronic illnesses. That's really important to understand as we're going through all of these genetics, that this is just a predisposition. It means your body's more sensitive to the effects of diet and lifestyle, but you can still mitigate that risk by making better diet and lifestyle choices. Now, HLA, this stands for human leukocyte antigen gene. This is the gene that encodes the major histocompatibility complex. So we talked about class 1 and class 2 MHC as being these flagpoles that the immune system has. The immune system cells use MHC class 2, and regular cells use class 1 MHC, and these are ways that the immune system can say, hey, look what I found, or how cells can tell the immune system, hey, I'm infected with this. So a variety of defects in this flagpole protein are linked with autoimmune disease. And when you think about what that protein does, that makes a lot of sense that if something's not working right with that protein, that might impact how the immune system is either responding to an antigen or detecting an antigen. So the B8 variation of HLA has been associated with Graves' disease. The B27 variant of HLA has been associated with ankylosing spondylitis, postgonococcal arthritis, uveitis, reactive arthritis, seronegative spondyloarthropathy, iritis, psoriatic arthritis, Crohn's disease, ulcerative colitis, and ulcerative colitis-associated spondyloarthritis. The B47 HLA variant has been associated with 21-hydroxylase deficiency. The DR2 variant has been associated with lupus and chronic Lyme. DR3 has been associated with autoimmune hepatitis, Sjogren's, and Graves. DR3 and DR4 are associated with type 1 diabetes and Hashimoto's thyroiditis. DR4 is also associated with chronic Lyme disease. DQ2 and DQ8 are very strongly associated with celiac disease. Upwards of 97-98% of celiac disease sufferers have either DQ2 or DQ8. They're also associated with Hashimoto's thyroiditis and Sjogren's. DQ5 is associated with scleroderma, and DQ7 is associated with Hashimoto's thyroiditis. So we have this genetic predisposition where really one of the things that the genetic predisposition does is impact the immune system fail-safe. So you saw this thematic impacting how the immune system is going to detect autoreactive cells, autoantibodies. That's where genetic predisposition comes into play. But there's this other aspect of autoimmune disease that is critical, and that is this stimulation for the immune system to attack. And this is where diet and lifestyle are really the key actionable inputs to immune health, because diet and lifestyle, the wrong diet and lifestyle choices can really drive the immune system to attack, and the right diet and lifestyle choices, even if you've got tons of genetic risk genes, even though you've got that history of infection and autoantibody production, if the immune system's regulating itself well, you do not have autoimmune disease. So what stimulates the immune system? I mean, infection, certainly. Toxin exposure, poor detoxification. That's one of the ways that an MTHFR gene variant can sort of be a double whammy. Gut dysbiosis, increased intestinal permeability or leaky gut. We've talked about those already at length. Stress, insufficient sleep, being sedentary, or the other extreme of activities, sort of overtraining, engaging in exhaustive, intense activity. Nutrient deficiencies, which we're going to talk about length in week 2, vitamin D, iron, zinc, vitamin A, copper, magnesium deficiencies, and all of these things can drive inflammation. And then inflammatory diets, so diets that are high in sugars and sweeteners and oxidized fats, trans fats, omega-6 fats, processed food chemicals, preservatives, food dyes, but also the inherent inflammatory compounds in a lot of foods that are sort of traditionally viewed as healthy. Grains, legumes, nightshade vegetables, which includes tomatoes and potatoes and eggplant and chilies. These foods are inherently inflammatory. They can inherently drive the immune system. And we're going to talk about the compounds in those foods and how important elimination of those foods are in weeks 3 and 4 of this lecture series. So as we look at immune function and autoimmune disease, we're really looking at understanding all of the different aspects. We want everything to be regulated. We want everything to be efficient because you want a regulated immune system, but not a suppressed immune system, right? And a suppressed immune system is going to create an environment where you can develop cancer or you can be more susceptible to infectious disease. So you want an immune system that's doing all of these different steps efficiently. So remember, we have these sentinel cells that are living in our tissues that are waiting for a pathogen to wander by so that it can start stimulating the rest of the immune system. The innate immune system is that first responder. And the adaptive immune system is that very targeted responder. It takes a little bit longer to ramp up, but it's what allows the body to react in a targeted way. But remember, we can also divide the immune system into its effector cells, right? It's attacking functions and its regulatory functions, the part of the immune system that shuts everything down. Now, this attacking part, this belongs to both the innate and the adaptive immune system, and this regulatory aspect belongs to the adaptive immune system. You need both to be able to fight off an infection. You need that balance, and one of the things that we're trying to do with the autoimmune protocol is provide the gut health situation, the nutritional sufficiency situation, the hormonal regulation situation, where you can achieve that balance. And that way the body can effectively fight off infection, destroy cancer cells, but it's not attacking itself and creating autoimmune disease. Now, there are certainly some things that can stimulate the immune system that we have less control over. These are things to keep in mind for troubleshooting. These are things where you would work with a functional or integrative medicine specialist to deal with, but it's important to kind of go through these just from understanding all of the complex drivers of autoimmune disease. So H. pylori I mentioned as being a possible source of autoantibodies, but it also is a really interesting microorganism because it can directly influence how the immune system is functioning. So it interacts with the immune system by influencing what cytokines, or those chemical messengers of inflammation, are produced by macrophages and B cells and T cells. And this can drive either Th1 or Th2 helper T cell subsets, usually Th1, but it can actually flip back and forth. So it evades detection by our immune system by manipulating how well it's working. It also can stimulate the recruitment of inflammatory cells, such as neutrophils. That's one of the reasons why stomach ulcers is a possible complication of H. pylori. It also changes the stomach environment, so it can change gastric acid secretion. It can change the secretion of mucus in the cells that line the stomach. Again, this is one of the predisposers to ulcers and cancer. And of course, one of the things that you get is this chronic gastritis, this chronic inflammation. So they can stimulate both a dysfunctional adaptive immune response and also chronic inflammation. And those are two things that can drive autoimmune disease if you have the other predisposing factors. T. gondii, we've already talked about in terms of it being a previous infection can predispose us to certain autoantibody formation. But it also damages the intestinal barrier to have a T. gondii infection, and it induces a potent response of Th1 type 1 helper T cells. It also inhibits macrophages and dendritic cells, so this can sort of cause a sort of chronic secondary inflammation and immune activation, again driving the immune system. Cell wall deficient bacteria are getting recognized more and more as potentially the culprits behind lupus and sarcoidosis, and they're very, very difficult to detect. So this is a class of antibiotic-resistant bacteria. They can persist and remain latent, so they're not causing any symptoms inside your cells for years. And it's thought that actually this might be a factor in more autoimmune diseases than what's actually been tested in. They're very, very difficult to detect. But these might contribute to autoimmune disease by releasing endotoxin into immune cells, so specifically phagocytes, those eater cells, and causing them to release cytokines that drive type 1 helper T cell subsets. So concurrent infection can certainly drive the immune system, as can toxin exposure. We know, for example, that there's 38 prescription drugs that are linked to lupus. Some of them, in some cases, when you discontinue the drugs, lupus will go away. And in other cases, once lupus has been caused by that prescription drug, even discontinuing the prescription drug leaves that person with lupus for a long period of time. There are certain toxic pollutants that can increase the chances of autoimmune disease. This is one of the things that we see in communities built on sites where there's been chemical wastes in the water or in the soil. It's one of the reasons why we see an increase in autoimmune diseases in those communities. There's certain workplace hazard chemicals like silica dust that leads to a very high incidence of systemic sclerosis in workers who are working in silica dust environments. Smoking cigarettes increases risk of arthritis, in addition to many, many other health problems. If you are watching this lecture series and you have not yet quit smoking, that's step one. So that is your goal for this week, is to have the motivation to quit smoking, because that is not just contributing to autoimmune disease, but dramatically increasing your risk of just about every chronic illness. Pesticides are interesting because they are generally immunotoxic. They drive different T cell populations, they drive natural killer cell activity, they drive neutrophil activity, they can cause death of the thymus cells in the thymus gland, they can drive antibody formation from B cells. They have this huge collection of sort of immune driving activities, and while all of the studies that we have looking at this come from occupational exposure, so farm workers, we see a little bit in leisure exposure, so using pesticides in your garden. We don't have evidence that links the residual amount of pesticides that we might get from buying conventional produce in the stores. We don't have evidence that links that to autoimmune disease, but knowing that pesticides are immunotoxic and knowing that people with autoimmune disease have this genetic predisposition to being a more sensitive population, minimizing exposure to these makes a lot of sense. Ultraviolet radiation, while an essential component of our lives because it helps us synthesize vitamin D, we actually know that there is a relationship with vitamin D deficiency increases risk of a lot of autoimmune disease, but high UV, for example, can increase risk of dermatomyositis. Heavy metal exposure can drive the immune system, so we know that heavy metal exposure, especially mercury, cadmium, lead, aluminum, and gold, can drive autoimmune disease. Poor detoxifications, we've already talked about MTHFR variants, that can drive the immune system further as well. So there's a lot of different things that can, from our environment, that can stimulate the immune system, which is why it's then so important to focus on the things that we can control, how what we eat and our lifestyle choices impact gut health. Right? We've already talked about how leaky gut is a prerequisite for autoimmune disease to develop, or at least it's believed to be one. So whatever that we can do that can improve gut health is going to be helpful in mitigating autoimmune disease. The gut microbial environment is such an important modulator of our immune system. So whatever we can do to support a healthy gut microbiota is going to be essential in modulating autoimmune disease. Remember that having a diverse community of gut bacteria involving a lot of these wonderful probiotic strains like lactobacillus and bifidobacterium, these guys can help balance and restore that balance of regulatory T cells and effector T cells. They can help modulate the activity of natural killer cells, these cells that are impacting the sort of innocent bystanders, these attacking cells. They can even help protect us against other pathogens. Stress can drive the immune system. I mean, we're going to talk about all these lifestyle factors in a lot of detail in week 5, but stress is inflammatory. Stress drives dysfunction of the immune system. Stress affects T cell subsets. It's situation dependent. It increases inflammation. It impacts gut health. So being under chronic stress can basically cause a leaky gut. It alters the gut microbiota. It reduces sleep quality, which is important because sleep influences the immune system. Not getting enough sleep is inflammatory. Not getting enough sleep drives effector T cells and suppresses regulatory T cells. So not getting enough sleep is this other really critical aspect of this drive of the immune system to attack. And we actually see relationships between sleep disorders like insomnia and increased incidence of autoimmune disease. So having once or twice a week where you have a hard time falling asleep or staying asleep increases risk of autoimmune disease on average by about 50%. If you have obstructive sleep apnea, that increases risk of autoimmune disease by double. So we see this link between sleep and how synced we are with the day and night. So shift workers are at higher risk of autoimmune disease. This is a really strong link, and it's because sleep is profoundly important for immune function. And activity drives immune function as well. So being underactive is inflammatory. So being very, very sedentary is inflammatory. Overtraining is also inflammatory. It can cause increased intestinal permeability. So finding that wonderful balance in the middle where we're active all day, but we're not overtraining, we're not engaging in this exhaustive, strenuous exercise, this is really important for regulating the immune system. In fact, we see that regular activity at a moderate level reduces the amount of pro-inflammatory cytokines that are produced by the body. So it decreases inflammation that way. In fact, it may have a direct impact on the innate immune system through inhibition of toll-like receptors and a specific cytokine called interleukin-1. And the focus of week 2, in terms of causes of autoimmune disease, is going to be nutrient deficiency. So there's a tremendous amount of nutrients that the immune system needs to function normally. In fact, the immune system is a nutrient hog. It uses nutrient resources like no other system in the human body. And what's fascinating is that a lot of these nutrients are required for immune regulation. So it's required for that part of the immune system that is controlling the entire system. So when you're deficient in these nutrients, the first thing that breaks down is the ability of the immune system to regulate itself. The next thing that breaks down is the ability of the immune system to effectively handle pathogens. So you get this situation where the immune system is overactive, inflammation's going crazy, it's super insane, but at the same time, the body can't actually vanquish a virus or a bacteria very well, and it can't turn off the immune system very well. So nutrient deficiencies are a key driver of the immune system to attack. And we actually see this link between certain nutrient deficiencies and autoimmune disease. So for example, vitamin A deficiency is linked with alopecia, multiple sclerosis, and autoimmune hepatitis. Vitamin D deficiency is linked with lupus, type 1 diabetes, autoimmune interstitial lung disease, multiple sclerosis, rheumatoid arthritis, celiac disease, psoriasis, and inflammatory bowel diseases. Vitamin E deficiency is linked with psoriasis, vitiligo, alopecia, and rheumatoid arthritis. K2 deficiency is not necessarily linked with autoimmune disease, but we know that supplementation with K2 can be beneficial in multiple sclerosis. Vitamin B6 deficiency is linked to type 1 diabetes. B9 or folate is linked to cerebral folate deficiency syndrome, rheumatoid arthritis, Sjogren's, celiac, Crohn's, and ulcerative colitis. B12 deficiency is linked with multiple sclerosis, celiac disease, Sjogren's, Crohn's, ulcerative colitis, autoimmune atrophic gastritis, alopecia, and type 1 diabetes. Vitamin C deficiency is linked with lichen planus and idiopathic thrombocytopenia purpura. And zinc deficiency is linked with rheumatoid arthritis, multiple sclerosis, pemphigus vulgaris, Alzheimer's disease, autoimmune hepatitis, primary biliary cirrhosis, autoimmune thyroid disease, systemic lupus, and celiac disease and type 1 diabetes. Selenium deficiency is linked with Hashimoto's and Graves', pemphigus vulgaris, and lichen planus. Iodine deficiency is linked with both Hashimoto's and Graves', both autoimmune thyroid conditions. Iron deficiency is linked with rheumatoid arthritis, autoimmune gastritis, lupus, Sjogren's, and celiac. Magnesium deficiency is linked to lupus. Copper deficiency is linked to rheumatoid arthritis and pemphigus vulgaris. Phytochemicals seem to be beneficial. Deficiency is hard to measure, and it hasn't specifically been linked with autoimmune disease. But when we supplement with phytochemicals, we can improve autoimmune thyroid conditions, type 1 diabetes, and rheumatoid arthritis. And omega-3 fats, again, deficiency is hard to measure, but we know that supplementation is beneficial in rheumatoid arthritis, Crohn's disease, ulcerative colitis, psoriasis, lupus, multiple sclerosis, and autoimmune-mediated glomerulonephritis. Autoimmune diets are a key driver of the immune system, and this is one of the major tenets of the autoimmune protocol, is to understand what substances in food are driving inflammatory responses. We're going to talk about all of these in detail in weeks 3 and 4. Prolamins, agglutinins, saponins, and glycoalkaloids, anti-nutrients in general, digestive enzyme inhibitors, processed food chemicals. These are all compounds that are either inherent to a natural food like grains and legumes, dairy and nightshades, or are added to a food through processing and refinement that can drive the immune system. So what you need to know right now is that understanding that these chemicals are really key drivers of inflammatory responses is why there is a link between, such a strong link between diet and lifestyle. So addressing nutrient deficiencies is hugely important for regulating the immune system, but also removing these inflammatory stimulators in the food. Other things that are inflammatory that we get from diets: high sugar intake, sweeteners, so sugar substitutes in general are no better. In fact, they're generally worse. High omega-6 intake can drive inflammation, and alcohol has a variety of effects that can drive inflammation. So we look at this as a whole. We look at what causes autoantibodies to form. We can't control most of that. We look at our genetic predisposition to an immune system that's going to overreact. We can't control that at all. But we can look at the various things that are driving the immune system to attack. It takes a healthcare professional to help deal with persistent infections, workplace hazards, of course, that requires some sometimes challenging choices. But so much of these things that drive the immune system to attack are related to diet, related to lifestyle, stress and sleep and activity and nutrient deficiencies and inflammatory compounds in foods. These are all modifiable. And this is what is so exciting about understanding the causes of autoimmune disease, is because we've identified this critical link in the chain of events that is modifiable. And even once autoimmune disease is developed, what's super empowering is that we can change the foods that we eat and our lifestyle choices to remove that stimulus of the immune system to attack. So even though we can't forget how to create these autoantibodies. Once the body has created an autoantibody, it retains the ability to attack self forever. But if we can allow the immune system to regulate itself, remove the stimulus for the immune system to attack, that provides whatever attacked tissues there are the opportunity to heal, regain function. It stops the attack, so it stops this degeneration of whatever tissues are being attacked. It allows the autoimmune disease to go into remission, which is not a cure, but it feels like one because it means it's completely asymptomatic. And it not only provides us with an immune system that's regulating itself well for autoimmune disease, but an immune system that's regulating itself well to prevent all other chronic illnesses. So it really creates a situation where not only are we regaining our health, but we're protecting it for the rest of our lives.